Hello, we are GatorWorks, and this is our final presentation. My name is Bernard Krasuski.
And I'm Jason Beckman.
GatorWorks is dedicated to de-risking and developing baseline autonomous vehicle software for Gator Motorsports. Gator Motorsports competes in a collegiate design competition hosted by SAE every year by designing, building, and racing a scale formula car against other universities. With the recent announcement of a new driverless aspect of the competition, GatorWorks aims to build the baseline software, tooling, and knowledge required for Gator Motorsports to be competitive in this new category. My name is Bernard Krasuski. I'm the algorithms lead. I'm a senior at UF studying computer science. And as the algorithms lead, I'm responsible for developing the autonomous driving stack spanning perception, localization and mapping, path planning, and vehicle control.
I'm Jason Beckman, and I'm the simulations lead. I'm a senior here at UF studying computer science with a focus on embedded systems. And as the simulations lead of the project, I am responsible for simulating the car, its environment, and its interaction with the environment to allow for rapid testing and development. So here we can see the product architecture diagram. You see the simulation block kind of in the top center. The three main components of this are the physics simulator, the LiDAR simulator, and the simulation orchestrator, also known as ROS Bridge. And then tangentially, we have kind of a debug visualization tool, which is the human driving simulator, which is also called SimViz.
On the algorithm side, we have the autonomous stack reading from the ROS2 bridge, reading the data from the simulation from the ROS2 bridge. The perception pipe and node feeds into the SLAM node, which feeds into the path planning node, which feeds into the vehicle controller. Out of everything in our project architecture diagram, the only thing we did not finish is the mission picker. And instead, we opted to just implement the two most point heavy dynamic events, which is autocross and endurance. So that is what our path planner node plans for.
So my individual responsibilities for this project was implementing the simulation stack, as I mentioned before, uh, which allows for the testing and rapid development of the algorithm in a safe, cheap environment before we deploy it onto an actual physical vehicle, which takes a lot of time, is expensive and dangerous if done improperly. As mentioned before, this includes the physics simulator, the LiDAR simulator, the ROS bridge, and the driving simulator. The physics simulator is primarily responsible for simulating all of the rigid body physics of the car uh, and the tires. Um, this involves tracking all of the rigid bodies and constraining them to each other, and also simulating dynamic elements such as the motor, the springs in the suspension, the dampers in the suspension, and the steering rack. The LiDAR simulator simulates a multi-beam spinning LiDAR by casting out rays into the virtual scene and measuring the distance from the LiDAR module to the point of intersection, essentially how a real LiDAR will do it. It additionally adds Gaussian noise to the measurements to more realistically simulate the LiDAR module and the environmental noise from things like sunlight. And then finally, the ROS bridge uh, instantiates the physics simulator and the LiDAR simulator, synchronizes their state, and ships all of that data to and from ROS. Additionally, I also helped implement a Stanley controller, which is the main vehicle controller and keeps the vehicle on the path. And I helped Bernard throughout the process of him developing the algorithms and stress testing them.
As algorithms lead, my individual responsibilities were to create the perception pipeline, the extended common filter landmark SLAM, and path planner and vehicle controller. I was able to implement the first three of these, and Jason helped me implement the vehicle controller node. The perception pipeline processes raw LiDAR point cloud data provided from the LiDAR simulator and publishes range, bearing, color, range covariance, and bearing covariance data. The extended Kalman filter landmark SLAM node consumes the cone data published by the perception node, as well as simulated inertial navigation system data. and outputs estimated vehicle pose and estimated cone map locations. The Pathfinder node consumes the SLAM cone map and runs a Delaunay triangulation on it. Using the Delaunay triangulation, we extract valid cross-track triangle edges and plot a path down the midpoints of these cross-track edges. And then we use a symbol point mass model to calculate the maximum acceleration the vehicle can withstand in each direction. And then from that, we append a valid velocity per path point. And then we also create the path to be 10 meters in line and behind the vehicle pose, and that's published for the vehicle controller to consume. For the demo, we're going to append a video we recorded about 5-10 minutes ago, just because all these algorithms are very CPU heavy, and with Zoom running and recording, we cannot, they don't have enough CPU to actually run. So we will append the video. And yeah, thank you very much.